Okay. I want to take a look at this and think of 3 plus I as 3 plus 1I as 3 comma 1. So we're co-opting the axes. Instead of an input axis and an output axis, we're now going to just describe complex numbers by doing a real axis and an imaginary axis. Notice that means, unlike functions of real numbers where you have one dimension for the input and one dimension for the output, imaginary complex numbers basically need 2 coordinates just for the input. So a complex function would need a 4-dimensional graph. Yeah, that's why we don't go there. But we are just going to be graphing the individual complex numbers. So. Okay, so 3 plus I, 2 plus 5I.
Plotting the point.
Well, do the arithmetic and you see five plus 6I. Let me plot that in blue. What on earth does that have to do with anything? It's much clearer with what we call a vector. And that is thinking of 3 plus I, not just as a point floating in space, but as a way to get from the origin to that point. And then if I take 3 plus I and take a copy of go right 2 and up 5 from it, and you take 2 plus 5I, and take a copy of right 3 up 1, then it turns out the sum is the diagonal of that parallelogram. They also call this the head-to-tail method because you put the head of the first vector joins to the tail of the second vector. So, okay, so let's just plot some of these. 2 plus 3I and negative 5 plus 2I. Again, we're going to be plotting the vector 2 comma 3 and the vector negative 5 comma 2. Let's see, 2, 3 and negative 5, 2. Again, if we're thinking of them as vectors, we're thinking of them as motions. Right 2 and up 3. And then left 5 and up 2 from there. Okay. And if you, similarly, if you go left 5 and up 2, and then go right 2 and up 3 from there, you end up at a new point, which is the sum of those two. Let's see. 2 plus 3I plus negative 5 plus 2I. Negative 3 plus 5I. Is that where the blue dot ended up? Yes, it is. How cute. The other thing about these pictures is that we can get what is called the absolute value, or the length, or they sometimes call it the modulus, but so 3 plus 2I, don't include the 3, don't include the I, so 3 squared plus 2 squared, square root of 13. So notice that if I plot it as right 3 up 2, square root of 13 is the length of that vector. And that means, since this is right 2 and down 3, isn't that the same distance away? I mean, it's in a different direction, but it should end up being the same distance. Don't forget, when you're squaring negative numbers, put parentheses around them. Don't put the I in. Sure enough, 2 in the real direction and 3 down in the imaginary direction. That distance away is square root of 13. 29, not 21. What about 4i? Let's think. Real and imaginary. 4i is actually 0 plus 4i. It's 0 in the real direction and 4 in the imaginary direction. And so if I Pythag it, I get a distance of 4. Is this thing 4 units away? Sure enough, it's 4 units away in the imaginary direction. So a purely real number, a purely imaginary number, you don't actually need to do the Pythag theorem. It's really the absolute value, and scrape off the I if necessary.